Hey guys, this is my Lab 5 report on magnetic braking of Faraday's law. The purpose of this lab was to collect observational data of a magnet falling through a tube of aluminum foil and then model the interaction in a computational model. We would then compare each one's results and see if there was any discrepancies. In terms of the results that we got, the observational model had an average time of 0.718 seconds to fall through the tube, while the computational model calculated it to be 0.479 seconds to fall through the tube. And then obviously this was with our magnetic dipole moment from lab 3, but I'll get into this other part later. So in terms of fundamental principles, we used Faraday's law, which is shown here, magnetic flux, which is shown here, and then since a bar magnet is a dipole, we used the iteration of Boyd-Swart's law for a magnetic dipole at any point in space, and then combining these three principles, we came up with this equation. We need to know Ohm's law, Newton's third law, Newton's second law for the updated velocity and updated position equations within our code, and then the magnetic force by a loop, which was shown here. And then once iterated with all our dipole moments, came out to be this. So in terms of the experiment, here's an observational model on the right to show what was actually occurring with a magnet falling through the aluminum tube. So the system is the falling magnet, the surroundings is the aluminum foil, and the Earth, since we were assuming these were the only two forces acting and interacting with the system. And then the initial conditions are shown here. The length of the tube was 0.38 meters, the width of the tube was 0.004 meters, the inner radius of the tube was 0.015 meters, the magnetic dipole movement from lab 3 is 1.985 ampere meters squared, and then the mass of the magnet was 0.024 kilograms. So in terms of the procedure, the bar magnet was marked at the North Pole, and then the initial conditions, as I showed on the last slide, were gathered. It was dropped through the tube 5 times, and then each time we extracted the time it took to fall through the tube. We took the average of these 5 trials, and then this average would be used for comparison. And obviously the average was 0.718 seconds, as I said before. In terms of the code, I only included what I changed, which was the initial conditions shown here, the functions for deflux, dt analytic, and dipole shown here. I didn't change this, but the bar magnet was from rest, so this was 0, as well as the ring current. This was the simulation loop, which I didn't really change anything in here except for the F grav vector and the ring current, which I showed in the last slide. Then this was the magnetic field and magnetic force on the ring shown here, as well as just changing F net and including our updated position and velocity functions. So in terms of the findings, as I stated before, the observed model got an average time of 0.718 seconds, while the computational model was 0.479 seconds when it had a magnetic dipole moment of 1.985 ampere meters squared. This can be seen over here, as well as the velocity versus time graph for this run. I wanted these to equal the same, and I kind of wanted to see how much of a difference in the dipole moment it would take. So when it was done with the dipole moment of 2.569 ampere meters squared, which can be seen down here, we got the same results as our observed model. Thus, it can be concluded that our magnetic dipole moment for a bar magnet from lab 3 was likely wrong, and that this new one was probably more accurate. In terms of sources of error, there was contact, which led to friction between the magnet and the tube in the observational model, which could slow down the speed of the magnet while falling. There could have been timing errors that led to longer times, and there could have been other forces acting. Since we only assumed 2 were acting on the observational model, this could have skewed our results. In terms of the discussion, a nearly zero resistivity would equal zero resistance, and thus a large induced current due to Ohm's law. This in turn would lead to a larger magnetic force, and would also make the magnet experience a larger magnetic force, thus causing it to fall with less speed and take longer to travel through the tube. If there's holes cut in the tube, since the tube is a series of continuous rings and the induced current flows through these rings, this would reduce the induced current. This would make the magnetic force felt by the magnet less and would cause it to fall with a greater speed, taking less time to travel through the tube.